You're verifying.
We were verifying the theorem when the function was f of x equals 2x minus x squared for the interval of -2 to -1.
-2 to -1. Okay, cool. So the first thing that you would do is say that it was continuous, right? F is continuous because it's a polynomial. And the second thing you would do is find f of -2 and f of -1. So let's see, looks like f of -2, what's that? -4 minus 4, so -8. And f of -1 looks like that's -2 minus 1, so -3. Everybody good with that?
Yes.
Okay, so then what we would need to do is go in and say that for any w that we choose that is between -8 and -3, there's a c value that's between -1 and -2. And we know that f of c, which is 2c minus c squared equals w. And that would give us -8 is less than 2c minus c squared is less than 3. Does that make sense so far, Joshua?
3 or -3?
Oh, sorry, -3. Yeah, sorry. But good so far, other than me forgetting the negative there?
Yes.
Okay, my guess is you got to there and then struggled to solve for c. Is that accurate?
Yes.
Okay, so what you need to do first off is recognize that this is a quadratic and that there are 3 different ways to solve quadratics, right? One is the quadratic formula, which is going to be a huge pain within a compound inequality. One is by factoring, well, setting it equal to 0 and factoring it, right? But setting it equal to 0 is going to be difficult with 2 different numbers over here. So our best bet is the third method, which is completing the square. And so if we want to complete the square, we need to have a coefficient on the c squared of a 1. So if I divide everything by -1, that'll give us this. Would you agree with that?
Yes.
And then now we can complete the square. So if I have c squared minus 2c to complete the square, we need to add a +1 in the middle there, which means I got to add a +1 and a +1 over here. So I'm going to get 9, and I'm going to get 4, and then I'm going to get c minus 1 squared. Does that make sense?
Yes.
Cool. And so then when I square root, I can either take the positive square root or I can take the negative square root. Or if you need to, when you're doing a problem like this, you can actually take the positive square root on one side and the negative square root on the other side. But in our case, we need it to be between -2 and -1. So it looks like taking the negative square root's our best bet, because then when we add 1 to each of those, we get the right inequality. I guess I wasn't going to do all of that, but then I did it anyway. So does that make sense?
Yes. Thank you.
Yeah. Anybody else have any issues with that one, or everybody okay? Quite a few people sent me messages and remind about that one. Don't forget, you can send me messages and remind if you're having difficulty with the homework. I usually get back to people usually within 10 or 15 minutes, but sometimes it might be an hour or 2, but usually get back pretty quickly. All right, the other one was the piecewise function that had 3 different pieces to it. Is that right? Can you read to me what that was, just since I don't have it up in front of me?
F of x is 2x plus 1, where x is less than or equal to -2. Ax squared plus b, where so it's -2 is less than x, which is less than 1, and then natural log of x, where x is greater or equal to 1.
And we want to prove that it's continuous for all real numbers, right? So first off, look at each piece of this and the domain that it's sitting on. Is 2x plus 1 continuous for all numbers less than or equal to -2? the answer should be yes, right? This is just a linear function, so this is continuous for all values that are less than -2. This is a parabola. It should be continuous for any numbers, right? So it's continuous from -2 to 1. And natural log of x is continuous if you're greater than 0, which we are greater than 0 here. So it's continuous from -infinity to -2, and it's continuous from -2 to 1, and it's continuous from 1 to infinity. The question is it continuous at -2, and is it continuous at 1? So we're only really concerned here about these breaking points in between, where it switches from one piece of the function to another. So we need to make the limit as x approaches -2 from the left of f of x equal the limit as x approaches -2 from the right of f of x, because that will make the limit as x approaches -2 exist, right? And if that limit exists and it's equal to the value of the function, which it clearly will be, because if I make the limit from the left equal the limit from the right, it gives me the limit that should be equal to the value of the function at -2. You agree with that?
Yes.
Okay, so that's our first step. 2 times x, which is -2 plus 1, needs to equal a times -2 squared plus b, or this becomes -3 equals 4a plus b. So that in itself is not enough to determine what a and b are, but luckily we've got another piece to this, which is we need the limit from the left of 1 to equal the limit from the right of 1, because we also need it to be continuous at 1. And so then the limit as we approach 1 from the left ought to be a times 1 squared plus b, and the limit as we approach 1 from the right ought to be the natural log of 1, which gives us a plus b equals 0. And so now we've got 2 different equations that involve the variables a and b. And it's just a system of equations we should be able to solve. We'll say a is equal to -b. If a is equal to -b, then this ought to be -3 equals -3b. Sorry, getting ahead of myself. -4b plus b, or -3 equals -3b, and b equals 1. And if b equals 1, then a must be -1. So there's our definition of continuity, right? The limits equal each other, which means the limit exists, and we know that the function exists and equals that same value at each of those points. Therefore, it's met the 3 criteria for a function to be continuous at a point for both those points.
Okay, thank you. Yeah, I just wanted to make sure that that was like enough to like using the because I guess I got confused on use the definition of continuity to justify your answer, because I did this, but I didn't know if that was like,
Yeah,
using the
you.
definition of continuity.
Yeah, I mean, it'd be nice to like really write out, okay, so the limit as x approaches -2 equals, this, and the limit as x approaches 1 equals this, and the value of the function is this, and the value of the function at 1 is this, and they all, you could write it all out and show that they're all true and they all equal each other like that. But this is good enough for me for now.
Okay, thank you.
Yep, no problem. All right, so let's get going with what we've been working on the last couple of days, or the last day, I suppose. So we're going to try and find all instances of when the slope of the tangent line to f of x equals 1 over x is equal to -1/4. So first off, what is the slope of the tangent line? What does this mean? What is the slope of the tangent line? How do we find that?
Use the derivative.
The derivative, right? And how are we finding derivatives? We are finding them by doing the limit as h approaches 0 of f of x plus h minus f of x all over h. So our question is when does this, or this function, equal -1/4? That's our question. So how are we going to go about figuring that out? Well, we need to find this limit. So this should be the limit as h approaches 0 of 1 over x plus h minus 1 over x, right? F of x plus h minus f of x all over h. And how do we simplify that down?
Make the numerator have the same denominator.
All right, make the numerator have the same denominator. So that'll be x times x plus h. So we'll put an x over an x times x plus h minus an x plus h over an x times x plus h all over h over 1. And that over h over 1 will flip and multiply by 1 over h. So that h will go into the denominator. And we've got the limit as h approaches 0 of x minus h, if I distribute the minus sign through it, over x plus h. Good or no?
Yeah.
All right, so now we have the limit as h approaches 0 of -h over h times x plus h, or a limit as h approaches 0 of -1 over x times x plus h. Good or no?
Good.
All right, as h goes to 0, x plus h just becomes x, and what do we end up with? -1 over x squared. So this is the derivative of 1 over x. The derivative of 1 over x is -1 over x squared. And we want to know when does that equal -1/4? Well, that would be when x is
Positive or -2.
positive or -2. So that's our answer. Now it might be kind of nice for us to see what this really means on the graph. So it didn't ask us for this, but what would be the value of our function at 2 and the value of our function at -2? Should be 1/2 and -1/2. Would you guys agree with that?
Yes.
All right. So if I wanted to write the equation of the actual tangent lines that have that slope, it should be y minus the y value equals the slope times x minus the x value. Or y minus -1/2 equals -1/4 times x minus -2. So let's take a look in Desmos at what that looks like. +2, not -2. And so 1 over x is this purple one, right? And then we've got our two tangent lines. They both have a slope of -1/4. And clearly this one touches the function at x equals 2 in just that one point. And this one clearly touches this function at x equals -2 only at that one point. They're tangent to the function there. Good or no? Everybody see how all those things sort of work together and make these tangent lines that have this slope?
Yes.
All right, at least somebody's answering me. That's great. All right. Next thing that we need to talk just a little bit about is something called the normal line. It's another thing that they'll often ask about on the AP test. The normal line to a curve at any point is just the line that is perpendicular to the tangent at that point. Right? So if we went back, actually, we'll just real quickly go back here to Desmos. If I wanted the normal line, I would just change the slope here from -1/4 to what?
+4.
+4. So if I were to do that, there it is, right? Sure looks like it's perpendicular there. It's perpendicular to the function, perpendicular to the tangent line at that point of x equals 2. And I could do the same thing with the other one if I wanted to. These would be the normal lines at these points. Okay, so that's all a normal line is. It's the one that is perpendicular at this point. Okay. So if we were to ask for a normal line, the first thing we'd probably want to find would be the slope of the tangent line. And if we can find the slope of the tangent line to write the equation of the normal line, all we'd have to do is take the opposite reciprocal of that slope. Everybody good with that?
Yeah.
Yeah.
All right. So if we want the normal line, let's do that. Let's find the slope of the tangent line to x² + 1/x at x equals 1. So if I want to find the derivative of x² + 1/x, let's separate this and do each one of these separately. Okay? That's going to make our life a little bit easier, I think. We're going to look at the limit as h approaches 0 of x + h² minus x² over h plus the limit as h approaches 0 of 1/x plus h minus 1/x all over h. And I'm sure you have a good idea of why I decided to separate it into two different ones, probably. What's the reason why I decided to separate into two different ones?
We already did the work for the right.
Yeah, we already did that one, right? This one right here is -1/x², right? We just did that on the last problem. So all we got to do is this one. So this is the limit as h approaches 0 of x² plus 2xh plus h² minus x² all over h minus 1/x². So it's the limit of this and then minus the 1/x². And just like all the other ones we've done, all the terms that don't have an h in them cancel out. Divide the other terms by the h. So we get the limit as h approaches 0 of 2x plus h minus this 1/x². And as h goes to 0, what do we get? 2x minus 1/x². This is our derivative. This gives us the slope of the tangent line. So at x equals 1, the slope of the tangent line is what?
One.
Should be 1. What does that tell us about the slope of the normal line? It should equal
-1.
exactly the opposite reciprocal, -1. And all that's left is to figure out what is f of 1 so that we have a point. And what's f of 1? It should be 2. And so our equation should be y minus 2 equals -1 times x minus 1. And we can go into Desmos and graph this all and see what it looks like. So there's x² plus 1/x. And we have y minus 2 equals -1 times x minus 1. And if I were to draw the tangent line right here, which I could, right? I could just change this to a positive 1 in front of there, or just get rid of it, right? We can see there's the tangent line in red, there's the normal line in black or gray or whatever that is, and it's tangent to the function at 1, 2. Everybody okay with that or no? You guys are real talkative.
Yeah,
Okay,
we're
great.
good.
Okay, just making sure. All right, let's do one more of these and then we'll call it good for today. We're not going to, I had a bunch of extra ones here. We're not going to do this. Let's just do this last one right here. Let's find the equation of the tangent line and the normal line at x equals 4. So before we go through and find the derivative, what's f of 4?
2.
So we got the point, right? The point that we're looking at is the point 4, 2. And we just want to be able to write the equation of the tangent normal line, which means we need a derivative. So we'll set up our derivative using a limit as h approaches 0 of the difference quotient. And I'll write that out, and then you guys will tell me how to simplify it. All right, there it is, right? Root x plus h minus root x over h. How do I simplify that? Can I just plug in the 0? Does that give me a number, an answer, something in terms of x?
Indeterminate.
Indeterminate. So how have we dealt with indeterminate limits in the past, especially ones with radicals in them?
We multiply by the conjugate. All right. So what good does that do us? Let's find out. X plus, or root x plus h times root x plus h, as we distribute all this out, becomes what? Just x plus h, right? Root x plus h times root x plus h, it's just x plus h. And root x plus h times root x should cancel with root x plus h times negative root x, right? Leaving us with just negative root x times root x, which would be negative x. All over h times root x plus h plus root x, which simplifies down to what? Just an h up there. Which gives us the limit as h approaches 0 of 1 over root x plus h plus root x. Good or no?
Yeah.
All right, cool. As h goes towards 0, this becomes 1 over root x plus root x. And what's root x plus root x?
2 root x.
2 root x. Perfect. So this is the derivative of this, right? The derivative of root x is 1 over 2 root x. In fact, you're going to want to memorize that, but we'll worry about that later today. If I wanted to figure out the slope of the tangent line at x equals 4, that ought to be what? Ought to be 1 over 2 root x evaluated at x equals 4, which is
1 over 4.
1 over 4. And the slope of the normal line ought to be the opposite reciprocal, right? Negative 4. So we've got y minus 2 equals 1/4 of x minus 4 as our tangent line. And we've got y minus 2 equals negative 4 times x minus 4 as our normal line. Good or no?
Yeah, that's good.
So let's take a look real quick on the graph. There's square root of x. We should know what that looks like, right? We got y minus 2 equals 1/4 of x minus 4. Definitely looks like a tangent line, right?
touching it at one point, staying on one side of it after it touches it. And then the other one, y minus 2, we should know that we're definitely right here already. Our tangent line looked good, but there's our normal line going straight through. Any questions or issues, problems, complaints, concerns, queries?
Can you show the slide real quick again?
Sure.
All right, I just want to make sure I get that down. Thank you.
Mm-hmm. Any other questions or issues with that? So the first rule that's going to make our life much, much, much easier is that the derivative of a constant is 0. All right, and we talked about this yesterday, right? The derivative of a constant is 0. We drew like a horizontal line. We talked about the slope being 0. Remember doing that on Tuesday, I guess?
Yeah.
All right, so let's think about this in terms of this limit. Well, if my function is y equals c, some number, 7, 10, -2, pi, 35, doesn't matter what it is, right? Or instead of me saying y equals c, let me say f of x equals c. What is f of x plus h? Well, f of x plus h means take all the x's in your equation and replace them with x plus h's. Do I have any x's over here?
No.
No, so f of x plus h is just c, right? It's just that number, right? F of 2 is c, f of 11 is c, f of -5 is c. It's just this constant, this number. So f of x plus h minus f of x over h gives us c minus c over h, which is the limit as h approaches 0 of 0 over h, which is still indeterminate if I try to plug in the h for 0, right? Or plug in the 0 for h. But 0 divided by anything is always 0, right? Unless you're dividing by 0. And if h is approaching 0, is h ever equal to 0?
No.
So this can just be the limit as h approaches 0. And way back when we first started talking about limits, the limit of a constant is a constant. So the derivative of a constant is 0 because of how it works out when we do this limit. Good or no?
Good.
Wait, how is it 0 again?
How is what 0? Which
Um,
part? There are a lot of zeros.
So you're saying it's indeterminate when you plug in h for 0.
Mm-hmm.
But then how do you solve it for 0?
Well, I simplified 0 over h, right? We can simplify the things that we have inside the limit before we evaluate, if they can simplify.
Okay.
And 0 divided by any number, provided that h is not 0, gives you 0.
Okay.
True. And h is not 0. H is, in fact, anything that is getting close to 0,
okay.
not
Yeah.
0. So that's why we're allowed to do that.
Okay.
Good?
Yeah, thank you.
Now, this notation right here that I've written, this d over this dx, this means derivative with respect to x. That's how that's read. It's read as the derivative with respect to x of a constant is 0. Now, what does it mean for it to be a derivative with respect to x? Well, all that really means is that the variable, if there happened to be a variable in this equation that we have, and there's not, right, because it's just a constant, the variable is x. So for right now, if I ask you what's the derivative with respect to x of, x to the 3rd power, well, we're going to learn how to do that in a second really easily. It just means that to take this derivative, I have to have my variable be x. If there's any variables in here, they need to be x. Otherwise, there's a problem that we'll have to deal with and find another way to solve this derivative, which we'll learn how to do later. But if I asked you to do this, the derivative with respect to x of y cubed, this is not something that we can do
without some extra tricks that we are not going to learn for another week or so. So the derivative with respect to x just means that the variable in here needs to be x. Everybody good with that for now?
Yes.
Perfect. Good. People are answering. All right. Let's learn what's called the power rule. And this looks horrifyingly complicated, but it's really, really, really simple, actually. The power rule is going to allow us to take the derivative of a function x to a power. So x to the second, x to the third, x to the 100th power. And it's going to give us a really easy formula for it. And the way we're going to get it is by simplifying the difference quotient for x to the n. So f of x plus h ought to be x plus h to the n power, and then minus x to the n all over h. Everybody agree that this is the limit as h approaches 0 of the difference quotient for f of x?
Yeah.
All right, cool. Now, all of this horrific expansion out here, except at minus x to the n, this is the binomial theorem expanded for x plus h to the n. You don't need to know all of that. You know that you can get it, like you can get the coefficients, right, by using your Pascal's triangle and so on. True? These numbers n times n minus 1 over 2 factorial, these are just the values in Pascal's triangle. And it's just the way that they are derived. So you don't need to know this. You just need to accept and hope that I've told you the right thing. This expands out to x plus h to the n. Can we all take that leap of faith with me there and believe me that that's x plus h to the n powered? With all this infinite number of terms in there for however big n is.
Yes.
Yep.
All right, cool. So now let's do the simplification, which sounds like it's going to be awful, but is actually quite easy. First off, anything that does not have an h in it should do what?
Cancel.
Exactly, it should cancel. And let's see, this term doesn't, and this term doesn't. Those are pretty easy to see. What about everything else in here? This one's got an h, this one's got an h squared, this one's got an h cubed. All these ones with the dot dot dots should have h to the 4th and h to the 5th and h to the 6th, and so on. H to the n minus 1 and h to the n, right? Would you all agree with that?
Yes.
Okay, cool. So now that I've canceled out everything that doesn't have an h, and I do have an h in the denominator, what can I do to every term in the numerator? Should be able to divide them all by an h, shouldn't I? Since they all have an h in them, can't I divide them all by an h?
Yeah.
Okay, so what is n x to the n minus 1 times h divided by h?
Nx to the n minus 1.
And then this next one ought to be n times n minus 1 over 2 factorial times x to the n minus 2 times h. And then what about the next terms? I'm just going to write out all of this nonsense in here. The last term here becomes h to the n minus 1, right? Because if I divide h to the n by 1, h, that should be 1 less power of h, right?
Right.
Okay, cool. So as h goes to 0, what is nx to the n minus 1? Are there any h's in that?
It doesn't change.
Right, it doesn't change. It's just nx to the n minus 1. What about this one? It's a bunch of crap, n times n minus 1 over 2 factorial times x to the n minus 2 times
0.
0, which is 0.
0.
plus the next term, which is a bunch of crap, times 0, which is 0. And all of these terms just end up being a bunch of zeros. And all we're left with is that the derivative of x to the n is n times x to the n minus 1. This is called the power rule. It's the power rule because it's for x to a power, but it's also very powerful. No, nobody. All right, cool. So the derivative of x to the n is nx to the n minus 1. This is a rule that you need to know and memorize. It's going to make your life so much easier. You don't have to do any of this expansion with this difference quotient anymore for these after tonight's homework. So any questions on how we got there?
Would the power rule work if you use like a radical, but you converted it to a radical exponent?
It would work that way. Yeah, we're going to talk about that today. In fact, the cool thing about this power rule, and it's not proven with just this, and I'm not going to spend the time to prove it for all real numbers, but it works for any real number. So if I had x to the 1.2 power, I could use this same rule. If I had x to the power of pi, I could use this same rule. Our little proof here only proves that it works for positive exponents, like positive whole number exponents, but it can be expanded. There's ways to prove it for all real numbers. And so, yeah, good question though. Any other questions, issues, problems, complaints about that? No? All right, so this is the rule right here. The derivative with respect to x of x to the n is n x to the n minus 1. So what we want to do is we want to find some more derivatives using this rule. F prime of x, that little apostrophe there is read as f prime of x. This means the derivative of f of x. There are lots of different ways to notate derivatives, and so I'm just going to sort of have them in here, and I'll talk about each one as they pop up. But the derivative of f of x can be written as f prime of x. And if f of x is x to the 7th, using the power rule, the power comes out to the front, right? And then we have x to the 7 minus 1. Or the derivative of x to the 7th is 7x to the 6th. Good or no?
Yeah.
And my guess is you would all prefer doing that instead of doing a limit as h approaches 0 of x plus h to the 7th minus x to the 7th over h, and then expanding out the x plus h to the 7th into like this huge, long, annoying thing.
Yes.
Yes, I'd prefer that.
Yeah, it is much better. All right, so same thing here. Y prime, that's the derivative of y. What should that be?
Four x cubed.
4x to the 4 minus 1, 4x to the 3rd. Exactly. And what about the derivative of x to the 50th? This notation we've already talked about, right? That derivative should be
50x to the 49th power.
easy enough. And definitely a whole heck of a lot easier than writing out x plus h to the 50th and expanding that out using Pascal's triangle. That's a lot of work. It's much easier, yeah. Everyone good with those? You need to be able to do those, because I promise you they're just going to get more and more difficult. All right. The next thing that we're going to talk about is when we have a constant in front of a function. So we're going to say that we're talking about u here as a function, u of x. So a constant times u of x. If I want its derivative, that's the same as just taking the constant and multiplying it by the derivative of u.
So effectively, I can take that constant out of the derivative and multiply it in at the end, which should, I think, make sense because what is a derivative? It's just a limit, right? And if a limit has a constant in it, you can pull that constant out, right? If we wrote it out using this like long form, the derivative of a constant times the function u of x is the limit as h approaches 0 of the constant times u of x plus h minus the constant times u of x over h. And those constants, right, can come out and be a constant out in front of the limit. Then we just have this limit that we know to be the derivative of u of x. It's the constant times du dx. Good or no?
Yeah, good.
All right. So the derivative of 5x to the fourth should be the same as 5 times the derivative of x to the fourth, which ought to be 5 times 4x cubed, or just 20x cubed. And you'll probably notice that writing this out in 3 different steps is not super necessary. I could have just taken the 4, multiplied it by the 5 to get the 20, and then dropped my power by 1, which is what we'll normally just do. So this one on the bottom here, this is a derivative, another notation for derivative, derivative with respect to x of 11x to the 8th should be what?
$88x to the 7th.
Yep, everybody good with that? Or no?
Good.
Next rule is if I have 2 functions being added together, I can take their derivatives separately if I want. So the derivative f prime of x for this, if f of x is x to the 5th plus 3x cubed, ought to be what? Just take the derivative here, take the derivative here, add them together. What do you get? What's the derivative of x to the 5th? Should be 5x to the 4th. And what's the derivative of 3x cubed? Should be plus 9x squared. Good or no?
Good.
All right. What about this one? What should we get?
40x to the 9,
Plus
3x to the 5,
plus 25x to the 4th. What about the minus 2x? Minus 2x to the 1st, right? So that should become minus 2x to the 0. Well, what's x to the 0?
1.
1. So, right, this minus 2x, the x just falls off of it. It becomes minus 2. And then what about the plus 3?
Becomes 0.
It's 0, right? Because the derivative of a constant is 0. Good or no?
Good.
All right. So as somebody was asking a little earlier, is this okay for fractional exponents and negative exponents and all that? Yes. Okay. It can be applied to every real number. So if I want the derivative of x to the negative 1, that ought to be what? Using the power rule, multiply the negative 1 and drop the power from negative 1 to
-2.
negative 2. And if I wanted to, I could rewrite this as negative 1 over x squared, but I would take either one of those answers. And x to the negative 1 is 1 over x, right? That's the one we did earlier using the limit, isn't it? Didn't we do 1 over x using the limit earlier?
Yes.
And what did we get? We got negative 1 over x squared, right?
Yes. Yeah, wow, this power rule sure is powerful. Yes, it is, Max. My 7-year-old says it's not, but he's wrong. It is. All right, what about this next one?
Would it be -4 times x to the power of -5?
Yep. And if we wanted to write it as -4 over x to the 5th, that'd be cool too. But either one I will accept. What about the derivative of x to the 3/2? Three halves, x to the,
1/2.
yep. Or I could write it if I wanted as 3 root x over 2. And what about this one? We did this one earlier, right? We did the derivative of root x. But let's show using the power rule that it comes out the same. The derivative of x to the 1/2 should be 1/2 x to the -1/2. And what is an x to the -1/2 should drop into the denominator as a square root of x. And this is exactly what we got earlier, isn't it? For the derivative of root x.
Yeah.
Yep. Man, that power rule sure is powerful. Ha 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 ha. I'm just going to keep saying it until you all laugh about it. Ha 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 ha.
Ha 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 ha.
Ha.
There's 2 people. All right. Only 27 more to go. Memorize that rule. That's a good rule to know. The derivative of root x is 1 over 2 root x. Not that it's difficult to do using the power rule, but it shows up so often that it'll just be convenient to know it. Everybody good or no? Hopefully so. Because now I'm going to give you 2 minutes to find the derivatives of these two on your own. Ready, go. What did you get for the first one? Hopefully 2/3 x to the -1/3. And then -12 x to the -4. Is that what you all got?
Yes.
Hopefully. Yeah.
Do we need to simplify or
If you want to write it as 2 over 3 cube roots of x minus 12 over x to the 4th, you can, but I'm good with either way.
Okay.
You know, if this was the AP test and it was multiple choice, there's a possibility that, you know, they might write it either way. So you need to be able to do both, but I'm good with either one. So this one, what do we get? F prime of x equals x to the -4/5. And then what? Plus 10 x to the
-6.
-6, and then plus 6x cubed. Easy enough? Any questions, issues, problems, complaints? Blah, blah, blah. Everyone good?
Yep.
All right. Okay, let's do these two quickly together because we're starting to run out of time, and I was really hoping to get through all of the rest of this stuff that we have in here today, and I don't know if we're going to have time now. So we should already know the derivative of root x is one over 2 root x, right? This is a 5x to the 3/4. So what should that one become? Should become plus 15/4 x to the -1/4. And minus x to the 1/10 ought to become a minus 1/10 x to the -9/10. Good or no?
Good.
All right, and this one is an x to the negative 1/2, right? So its derivative should be negative 1/2 x to the negative 3/2. And the derivative of 5x cubed ought to be plus 15x squared. Any issues with any of these so far? Okay, so we've talked about derivatives, right? What the derivative is, it's the slope of a tangent line. Well, we don't just have derivatives, we also have second derivatives, so the derivative of the derivative, or third derivatives, the derivative of the derivative of the derivative, or fourth derivatives, or fifth derivatives, or 100th derivatives. We can take as many derivatives of a function as we want. We call those higher order derivatives, or higher derivatives. So just so you could see it, and I'm just going to quickly talk about this, and then if you want to copy these down later from the notes, you can. But you'll see these so often that you'll get used to it. If I have f of x, its derivative is f prime. Its derivative is f double prime. Its derivative is f triple prime. And its derivative is the fourth derivative of f. And so on, we call it the fifth derivative of f, the sixth derivative of f, the nth derivative of f. Okay. So after the first three, you do prime, double prime, triple prime, then you just start writing the fourth, fifth, sixth in parentheses. Same if you do y prime, y double prime, y triple prime, fourth derivative of y, and so on to the nth derivative of y. The next one, which we've used, is we use d dx, but dy dx means the derivative specifically of some function y. So dy dx is a derivative. And then this d squared y over dx squared, we just read this as the second derivative of y with respect to x. And the reason why the superscript of 2 is on the d for the numerator, because that's saying the second derivative, right? Two derivatives, that's why it's on the d. And down here, it's on the x because we've taken the derivative with respect to x both times. So this is the third derivative of y with respect to x, the fourth derivative of y with respect to x, the nth derivative of y with respect to x. So far good?
Yes.
All right, and then these ones, derivative of x, or derivative with respect to x of y, second derivative with respect to x of y, third derivative, and so on. Okay. So how do you get a second derivative from a first derivative? You just take its derivative. And how do you get a third derivative from a second derivative? You just take the derivative. So let's find the first four derivatives of f of x equals 2x to the fifth. So what is f prime of x?
10x to the fourth.
Great. And f double prime, the second derivative, ought to be
40x cubed.
wonderful. The third derivative ought to be
120x squared.
great. And the fourth derivative ought to be
240x.
240x. Everybody good there?
Yeah.
Yeah.
All right. Let's do these ones. The first derivative should be what should it be?
6x to the 1/2.
Second derivative should be
3x to the negative 1/2.
third derivative should be
Negative 3/2x to the negative 3/2.
and our fourth derivative should be 9/4 x to the negative 5/2. Good or no?
Good.
All right. Let's find the first four of this. Hopefully you guys are getting the hang of taking these easy power rule derivatives. What's the first derivative of 3x to the negative 2?
Negative 6x to the negative 3.
And the next derivative?
18x to the negative 4.
And the next derivative?
Negative 72x to, negative 72x in the negative fifth.
Okay, and the fourth derivative should be, what's 5 times 72? Should be 360, x to the negative 6. Easy enough?
Yeah.
All right, last one of these that I'm going to make you do, at least in finding 4 derivatives. And we'll go back to just finding one. F prime should be
100x.
100x. F double prime ought to be
100x to the power of -1.
no.
No?
100x to the first, right? Should
Yeah.
become 100 x to the 0, which is just 100. Everybody good with that just being 100?
Yeah.
Yeah.
All right. And what about the next derivative here?
X to the negative 1.
No,
0.
this is a constant. What's the derivative of any constant?
Oh yeah. 0.
What's the fourth derivative then?
0.
0, because the derivative of a constant is 0. What's the fifth derivative?
0.
0.
0. What's the sixth derivative?
0.
0. What's the 100th derivative?
0.
My 7-year-old son beat you to that. He said 0 before any of you did. You should all be ashamed. All right. Just kidding. You shouldn't be ashamed of yourselves. I'm sure there's a lag in the time that it takes you to hear me. Don't be ashamed. All right. Let's take a look at a new function, x to the 4th minus 2x squared plus 1. So I'd like to know, does this function have any horizontal tangent lines? Well, before we even try to figure that out, what is a horizontal tangent line going to mean? It means that the slope of the tangent line is going to be
0.
0. Well, what represents the tangent line and its slope?
The derivative.
The derivative. So in order to figure out if this has any horizontal tangent lines, we want to know when the derivative equals 0. So what do we need to find? The derivative. What's the derivative of x to the 4th?
Four x to the 3rd.
And the derivative of minus 2x squared ought to be minus 4x. And the derivative of 1 ought to be
0.
0. So all we care about then is, this is our derivative. We want to know, based on the context of this problem, when does that derivative equal 0? So let's find that out. How can I solve that? Factor out the 4x, right? Which gives us x equals 0 and x equals plus or minus 1. Everybody agree with that?
Yeah.
Cool. So that's where it has horizontal tangent lines. let's real quickly graph this function. All right, everybody see that at -1 and at 1 and at 0, if I were to draw the tangent line, it should look horizontal. And what happens to our function there? It either changes from being decreasing to increasing or increasing to decreasing, right? It has a turning point there. So these places where we have horizontal tangent lines are going to become very important to us as we look at the nature of our functions. If we wanted to know the equations of those lines, could we evaluate y at 0? Yeah, that'd give us 1. And if we evaluated y at 1, that would give us 0. And if we evaluated y at -1, that would also give us 0 if we plugged in those numbers up there. Plugged in 0, 1, and -1 to our original function.
Yep.
Yep. And so that would tell us that the equations of those horizontal tangent lines were y equals 1 and y equals 0. And if we go back to Desmos again real quick, y equals 1, there it is. It's tangent at this point. They may cross through it somewhere else, but at this point, it's tangent. And the same with y equals 0. It's tangent here, and it's tangent here. Everybody see that? Makes sense? Good with that?
Yep.
All right. We got one more problem today, and then we're done. We're actually going to finish. I thought we weren't going to. But... So I'd like you guys to take just a minute and see if you can figure this one out on your own. Ready, go. All right, so what is y prime here? If we're looking for the horizontal tangent lines, y prime should be x squared minus 4. And if we want to know when we have horizontal tangent lines, that should be when our derivative is 0, which should only be x equals plus or minus 2. Good or no?
Good.
Okay, cool. So we got x equals plus or minus 2. That's locations. If we wanted to figure out what the actual values were, we'd figure out what's y of 2 and y of -2. So if I plug in 2, that's 8/3 minus 8 plus 9. What is that, 11/3? And if I plug in -2, that's -8/3 plus 8 plus 9. That's 43/3. So let's take a look at the graph and those two lines and see if we did it correctly. So we have 1/3 x cubed minus 4x plus, what was it, plus 9, is that right? And then we had y equals 11/3. Looks like that is tangent right here, right? 2, 11/3, looks pretty good. And what was the other one? 43/3, I believe. Yep, looks tangent to the curve there. So we have two horizontal tangent lines, one at -2 and one at +2. Any questions on that? Everybody okay with that?